Here is my Ansys Fluent. I installed the last version, academic version of Ansys. And here in the left bar, we can see different choices. After we select the general model, the models of the flow, they are the models, the physical models devoted to the type of the flow, which are the processes, what are the turbulence model species, etc. Then we choose the materials, boundary conditions. At the end, when we form complete equation system, we must make a choice on the solution methods. So when I click to the methods, here I can see the list of choices. There are general schemes, like a scheme of pressure velocity coupling, for example. Here I suggest you to leave as it is, unless you know what are the other methods. Then the spatial discretization are devoted to solution of each of the flow equations present in our system. For example, calculation of gradients, how the derivatives responsible for the calculation of the derivatives will be, of the gradients will be made. Then how the pressure approximation will be made. Second order, how the momentum equation will be approximated. First order, for example, turbulent kinetic energy, dissipation rate, etc., and others. Depending on the models you are choosing here in the general tab, and depending on the list of the models you choose here inside the models, here from this list, new options can appear or some options would disappear. So this list of methods is adapting to the physical models you chose before. And these are just options responsible for the transformation of your system of differential equations into the system of the algebraic equations. Okay. So today I would like to give you the idea of what are these transformations, how they can be obtained from the physical point of view, from the mathematical point of view, and what actually to choose in which case. I will share with you another screen now to start writing things. And if you have some questions in the middle, please ask. So I will start writing you some kind of derivative we needed to try to solve inside our equations, inside the continuity, momentum, or energy, or other equations, for example, devoted to the turbulence model. Some derivative always happens. For example, I will write a derivative of the velocity, which we may found in various equations. Du by dx, for example, the partial derivative of the velocity in the x direction. As you know, computer does not solve the derivative as they are written in the mathematical form. They always transform them to their algebraic form. So here I will make some graphics as well to demonstrate how this transformation can be done using several different methods. What are the advantages and disadvantages of each of these methods? I have two coordinates. I have x coordinate, space coordinate, and u coordinate as the value of this function. And for example, I already have my mesh, so I have points. Okay, let's put some points here. Like this. And one more point probably. Okay, so these are the points, the values of the function in its corresponding coordinates. Okay, I will be interested to calculate at some point some arbitrary point I. Usually we denote as point I, point of the interest. And the other points we can denote in our space as point I plus 1. Then the previous point is point I minus 1. And one point behind is I minus 2. Okay, so what is the first order approximation, as we just saw in the one of the choices? First order approximation is when we join the points in our space by first order function, or the line is the linear function, right? The line. So this is the straight line between points. This is very simple way to approximate discrete points by function. Very simple linear function, right? It can be characterized by the inclination angle, for example, and is characterized by its distance from the origin at some point. You know the equation of line is very simple. So the derivative written for the line is very simple from the mathematical point of view and can be written as follows. We take the value of the function at point I minus the previous point and divided by delta x, the distance between these 2 points. Okay, this is delta x. For simplification, for the simplified model, we just use the delta x same everywhere. Of course, for our real mesh, delta x is not constant and is changing from one mesh point to another mesh point. But it's the idea remains the same, just mathematical model becomes more complicated when we choose not equal distance between points. In our case, it's just an example. We keep constant distance between points. So calculating using this first written formula here, what I just did, I took this point, difference between these 2 points, right? The previous point and this current point of my interest. I took the difference divided by the distance. So basically, I calculated the tangent of this angle here. This is my derivative, right? This is my derivative, which I have been calculated. But I did it to calculate the derivative at point I. We easily see that the inclination, this angle here of this line is different from the angle of this line. So depending on what is the method of approximation we choose, we can obtain really different derivative, even using the linear approximation. For example, if I will take this line of this point of our interest and the next point, I can also write the derivative in the following way. Du by dx at point I would be equal to the value of the function at the next point, I plus 1 minus value of the function at this point divided by delta x. This is also possible. Yes, it's possible. And it will, as you see, it can give us different value of the angle, different value of the tangent of at this point. Okay, but we are calculating for the same point. So depending on the method, on the points we are choosing for calculation of the derivative, the result will be different. So this is a linear approximation. We just make a line between points and we calculate the derivative based on these points. Another more advanced method of approximation is the second order approximation. Second order means that we are substituting the function not by the line, but by the second order curve, which is parabolic function. I will choose another color here and I will try to make a parabolic function. So basing on a parabolic function, we can describe much better our derivative in the point of interest. This is still our point of interest. And if we build a parabola using 3 points, because to build a parabola we need all 3 points, we can improve the quality of the approximation, and so-called second order approximation. So I will write you here what is the answer. The derivative calculate derivative based on 3 points parabolic function at point I would be equal to u at point I plus 1 minus u at point I minus 1 divided by 2 delta x. This can be obtained quite easily if you build this parabolic function, then you will obtain the derivative function in this way. It's done in many literature, in many books, especially my favorite, which is Anderson, Fletcher, Tannehill. And there you can see how is obtained this derivative. So it's the second order method, more accurate method. Okay, there are also other methods available in Ansys. As you may find, the most very common method is the third order approximation method. How is it made? It's also based on the same idea. We just needed to use more points to approximate our function. For example, I will use this point here, this. Based on 4 points on the curve, I can build the third order polynomial function, right? And I can theoretically describe better my derivative in the point of interest here. It's still point of my interest. I will try to make here, but I am not sure if it will look nice from the first attempt, but I will, if not, I will try to improve later. So sorry, there's some problem of writing here. So my third order curve will start to go like this, and that will have its maximum and will go like something like this. This is third order polynomial function. Maybe it would be better if I write the function. It's a plus bx plus c x squared plus dx cubic function. Some coefficients, a, b, c, d are constant coefficients, right? Okay, similar to this example, I will write my polynomial function for the parabolic function. It's a, okay, but will be not the same value of a. I will write just a1. This is a different coefficient, plus b1x plus c1x in square. And the linear function was very, very simple. The linear function I will write here, it's a plus bx. More detailed is the polynomial function, more accurate, looks like more accurate becomes the curve, because it takes into account more and more information as initial data to build this curve. But more and more complex becomes the equation. And in this case, we can also see what will be the derivative. Okay, I found it's equation 379 in the book, which is not exactly for these 4 points, because for different number of points, for different position of points, the equation would be different. It's written for another points. They are points I, then I plus 1, I plus 2, and I plus 3. For these 4 points, but there are also 4 points as we had before. But just to show you how complex becomes the function of the derivative, du by dx becomes 1 divided by delta x, 6 delta x here, and in the brackets we have minus 11 u at point I plus 18 u at point I plus 1 minus 9 u at point I plus 2 plus 2 u at point I plus 3. Okay, this formula is describing for us the derivative, partial derivative of function u at near point I based on 4 points, on this point, on current point, and the next 3 points. How this formula can be obtained, not just this one, but also the previous formulas, this one for the second order, this one for the first order, and this one for the first order, how they can be obtained. There are generally several methods described in the book. They are Taylor series method, when we split our function using Taylor series. They are the polynomial fitting, when we describe the function as a polynomial and then separate derivate from this polynomial function. There is an integral method, when we are integrating our flow equations inside the control volume, and we are then excluding derivate from this integral. And there is a so-called finite volume or control volume approach, probably. And then we apply our conservation law to the control volume and separate the derivate from this control volume. These all 4 methods are explained in the book. I'm not just saying that they exist. I also would like to give you the pages in the book of Anderson, Fletcher, Tannehill, so you could read, and the next time, if you have more questions, you could ask how these methods are working. I think they are not difficult, and they are very important for you to understand what method to choose when you are solving inside Ansys Fluent. Okay, it's the book pages from 60 to 76 from the book. Okay, so these methods. Now let's talk what method to choose and justify. Okay, the first method we saw is the linear first order approximation method, when we approximate just by the line. It's a blue line here. Is this method good or not? This method is definitely the simplest possible method that exists in the computational fluid dynamics, right? It requires just 2 points to calculate a derivative, and these are not the only advantages, that simplicity, that also it's a quite it's a predictable method, so-called monotonic solution. What is the monotonic solution? We are sure that using this method, we are not jumping over the parameters. For example, if I will give you a distribution of temperature, and we will use this first order approximation method to calculate the temperature derivative and calculate the temperature, in general, temperature distribution. Okay, I will give you very simple distribution of points like this. It's a temperature distribution in space. We see that in first points, temperature is constant, first 4 points, and then temperature goes down. So what should happen with temperature? It's quite obvious, right? The temperature between points approximated by first order method is changing according to the linear function. So we are not exceeding, we are not going over the limits of maximum and minimum values given by this point. So it's quite well predicted. And this is the last advantage of the first order approximation method. It's very predictable. If we will go to the second order approximation method and try to use a parabolic function to approximate, here we may face some trouble. For example, this point of our interest is this one here. This is a coordinate of our interest, and let's try to make a parabolic function around these points to calculate the derivative. So we will have something like this. Okay, this let's assume it's a parabolic function. Okay, it should be, I know it should be symmetric, but let's assume it's symmetric. It's just problem of my poor level of drawing. Let's assume it's symmetric. So what we see, if we try to approximate temperature by parabolic function, somewhere in this region, approximated temperature is higher than actual temperature given by points. What do you think is physically possible or not? I think temperature cannot rise from nowhere, right, and cannot exceed maximum temperature in the system because there is no source of temperature here in this region above the red function, above the red line, above the red line. So temperature cannot be higher than given by points. Okay. Same thing if we will try to see distribution of also temperature, for example, when we have the following data. Okay, I will make another graph of the temperature as a function of x coordinate. And in this case, I will have initially low temperature values, and then my temperature starts to rise. For example, we are heating the plate. We are heating the plate from one side. We heat plate from, or we heat gas from this side. We put an additional temperature here, or heat loads from here, and temperature starts to rise. First, it's a bigger temperature, then it drops, and then it's constant because it did not reach this point. Heat did not reach yet, not enough time to heat completely all the plate. Okay, so if I'm using the first order approximation, simple approximation, dt by dx is equal to ui minus 1 divided by delta x, I see no problem because all my points are joined by simple lines and nothing is going under or below the limits. But same time, if I again will try to build a curve of higher approximation order, like second approximation order, this is my point of interest. Okay, I will try to make this parabolic function. It will be like this. So I again see the region of temperature which is lower than possible temperature in my system, because when I'm heating the plate from one side, I cannot have a drop of temperature here in this zone. It's just because of the approximation level of the second order approximation. I have this drop mathematically, but I do not have this drop physically. So this is a difference between the approaches, because mathematically you can write anything, right? But physically this process will not happen. So based on second order approximation method, we cannot trust if we approximate, for example, temperature using this method, because somewhere temperature can or over jump over the level of maximum possible temperature like here, or can be lower than minimal possible temperature in our system like we have here, and this is physically impossible to obtain. Okay. In this case here we heat from this side, and the case of the right picture we heat from another side. So we cannot have in the middle temperature higher, and we cannot have in the middle temperature lower than minimal temperature in the system. These are the problems of high order approximation schemes, of high order approximation methods, and we have to be really, really careful working with them. So the question is when we can use high order approximation method, like second order approximation or third order, which is implemented in Ansys Fluent. The answer is the following picture, which I can show you. If you would like to use parabolic function, try to see how your parameters are changing in space. And then you will have a clear understanding what method could be used. For example, my velocity changing in space in the following way. I have small values, and then step by step they rise. Not linearly, it's a kind of progressive change of the velocity, increase of the velocity, right? But what I can see, if I build the linear function, it will be something like this. Very, very smooth rise of the flow property, right? Linear function, first order. When I will try to build the parabolic function around this, it will be practically same curve. And if I will try to build the third order approximation here based on more points, it will be also very, very similar curve. So what's the difference between this red line, between the orange line, which is second order? Okay, second order, then I will put third order, and the blue one I will put the first order. Somewhere here I will see my blue color and first order. So first order is the straight line, second order just parabolic function, second order, and third order is parabolic function based on 4 points. You basically see no difference by eye, but the computer, when it calculates, it will see a tiny, tiny difference between all these lines, and it will say you definitely that the accuracy is higher and can be really much higher if you use higher and higher approximation order. So for example, from first order to second order, you will see significant reduction of the simulation error, of the calculation error. From the second to third order, you will see more improved solution. Okay, so in this case, it's worth to use higher order approximation in case when you have a smooth change of the flow properties, flow behavior. And for us, what does it mean from the physical point of view? Smooth change is something of low energy flow, something of flow near the boundary layer in a low velocity. So let's already separate such tasks. I would like to do it first to recommend the first order, and then I will recommend second order for another types of tasks. So first order methods we use when we have a picture similar to this and to this picture, when we have a big gradient of flow properties change. So first order is usually high energy flow. That means that high Mach number. And as a consequence, it can be also shock waves. Okay. High Mach number can be subsonic high Mach number or can be supersonic high Mach number, which provokes the shock waves. You know, even for the subsonic flow, if you have a geometry compatible to create transonic flows, the shock wave also can appear, even if the infinite Mach number is subsonic, something like 0.8. So first order we use not just for these two cases. Very often we use them with the chemical sources or energy sources. Why I say energy sources? Because usually these energy sources can be of a very high magnitude. For example, having a chemical process of combustion, you can have the energy release of one order of magnitude of the incoming energy, and this changes significantly the distribution of the flow, and then only first order method can work appropriately with these methods. There are also other models which we can discuss, other types of the flow, and I think they will come to discussion a bit further while we are progressing in aerodynamics. And now I would like to list some number of models or types of the flows which are compatible with the second or third order approximation scheme that you can choose in the Ansys Fluent. So I will write second plus order. So second and second or third, it's should be not so much different. So as I told you, second order we choose for the smooth flow, right? Smooth flow is incompressible flow. Incompressible. Also the boundary layer in subsonic flow. Boundary layer in the subsonic flow. So all your simulations which you make in the first semester in aerodynamics, you can do using second or third order approximation. But first of all, I will just recommend you try first order approximation. Maybe it will be already satisfactory. If it does not satisfy you with accuracy, I mean convergence with experimental data, probably you need to increase to second order or third order approximation method. Disadvantage of second and third order approximation method are also increased computational resources required to perform the calculation. Since formulas are bigger, you need more calculation time. I think now the Green-Gauss method is another discussion, is another big question. You can keep it for the first attempt of simulation as it is by default, because usually Ansys determines default method as the suggested method is the default method. So no need to change these methods from the beginning. There are suggestions how to choose the method of solution, and they are based on the experience we may find in the literature, in the articles of the numerical simulation of the airfoils, of different airfoils. They suggest different methods, different models. I suggest you to search for these informations and to understand for which types of simulation, which method is being used. It's very, very important. The coupling method actually is something different with respect to the approximation of derivatives we discussed today. Is the method how we join a relation between, I think, velocity and pressure, and it's outside even of the discussion of the course. But if you are really interested to know about the method of the coupling, we could one day we could discuss this as well. But I think now it's not so important to be discussed. Just keep as it's recommended. There are totally 3 different methods of coupling inside the model, inside the implemented mechanism of the Ansys Fluent, and you can see which is closer to your experimental results. The goal for you, the main criteria to evaluate which method is better, is the method which corresponds to your experimental data. Once you have a great accuracy, once you have practically no error, it means that you found the best method to simulate your airfoil. And it must be not just one point, but it must be in all points for all the angles of attack, right? Usually I recommend 4 or 5, at least 5 points, 5 different angles of attack to calculate. So if you chose this coupling method and it fits perfectly in all points, so keep this method. If it does not fit, change the method to another, try to see what is the difference. But before trying to simulate, just go to tutorial of the Ansys. It's a big tutorial. Usually we can see all the information about methods there. And try to see for which types of tasks it's being developed. When we are looking to the experimental data on the airfoil, you can usually see the following. For example, lift coefficient distribution. I will make some simplification, okay? This would be my angle of attack. Okay, this would be my CL. And the curve is something like this. And it's not the curve, but it's formed by points for different angles. The values of the lift coefficient are given like this, okay? And if they are experimental points, it's usually written somewhere in the corner or somewhere should be written. Let's assume, for example, Reynolds equal 310 powered by 5. So this all experimental data is taken for the Reynolds 310 powered by 5. If you simulate another Reynolds number, you will receive different data. Because as you remember, to have same lift coefficient in the experiment or in the simulation for different types of the airfoil CL, you need to have the same Mach number and you need to have the same Reynolds number and angle of attack. Angle of attack you control by defining it inside the Ansys Fluent when you are starting simulation. Mach number is 0, is not important for us because we are working with the incompressible flow. So the most important thing is the Reynolds number. Okay, Reynolds number, we need to have the same as we had in the experiment and we have in our numerical simulation. We must also have the same Reynolds number. So if you will open the program, Ansys Fluent, I will not open again because it's useless. You will see there is no field in Ansys Fluent named Reynolds number. So you will not find any place inside Ansys Fluent to put Reynolds number inside your simulation. So you cannot put directly Reynolds number inside your simulation. So you can do it just explicitly. How to make it? We need to remember that the Reynolds number is something like velocity, right, multiplied by the density and multiplied by the size and divided by the viscosity coefficient. Something like this. I think it's nu or mu. Okay, no matter. We find the formula, okay, where the density is the density of the flow inside our simulation. C is the Hort. It's infinite, okay. V infinite, the velocity of the flow, and C is the Hort, the size of the airfoil. And another limitation is this, Mach number approximately 0 is the incompressible flow. So we must have, if we go to definition of Mach number, which is velocity divided by the speed of sound for incompressible flow is smaller than 0.3, is basically the same as we write that V infinite is smaller than 100 meters per second, agree? Because speed of sound is approximately 300, so I just divide and I obtain that maximum possible velocity of our simulation is 100 meters per second if we would like to keep our flow inside incompressible region, incompressible. So we have velocity limitation, which we can put inside this formula. And the density for free stream is also defined. Its standard density is 1.23 kilogram per meter cubic. And the viscosity is also standard for the air. Just let me remember, I think I'm making the same error and I am calling the viscosity by viscosity coefficient. But okay, let's assume that this is the viscosity which enters inside the formula. And it's equal to 1.8 10 powered by minus 5, something like this. And if it's not the correct value, we can always see in the standard atmosphere. But I think something similar to this. So from this formula here, the only unknown is Hord, right? And the Reynolds is 310 powered by 5. So when I will write, let's try. When we write 310 powered by 5 is our Reynolds equal to velocity 100 meters per second multiplied by 123 and multiplied by C divided by 1.8 10 minus 5. 10 minus 5, something like this. I think here we can already simplify something, right? This 10 minus 5, we can cancel with 10 powered by 5. And from here, we can see that Hord will be equal to how much? Is we are multiplying this 3 multiplied by 1.8 and we divide by 100 and we divide by 123. So it's basically 123, something like this. 0.044 meters, so it's 44 millimeter Hord. But who wants to calculate to simulate 44 millimeter Hord? It's completely ridiculous. And we have to consider another thing, that when our flow is moving, I will make the airfoil, and to remember you some theory from the airfoil, that this V infinite, if it's some value, for example 100 meters per second, that then somewhere on the upper part of the airfoil, our V1 at point 1 can be higher than V infinite and can be much higher, like 20-30% higher than V infinite. So it will be bigger. What does it mean to us? That V infinite of 100 meters per second at infinite distance from the airfoil, we never can set because of this process of flow acceleration near the airfoil, where we already start to be inside compressible flow, so we cannot use incompressible flow mode. We need to decrease this value, not 100, but we will use something like 50 to be safe. For example, if I choose to have equal to 50 meters per second, calculating again by the same formula, it basically will increase 2 times my Hord. I will come out with Hord of 0 0.88 meters. So 88 millimeters, right? It's already closer to my 100 millimeters than I have inside my example of the simulation. Agree? So we have 50 meters and 0.088. So we have several possibilities. Or we have this size airfoil and we set as initial velocity this value, or we do opposite. We have a horde of 0.1 meters, and we decrease a bit more the velocity. Proportionally, we decrease the velocity proportionally. So V infinite would be, in this case, 50 multiplied by 0.088 and 0.1 here. Oh, we can do this calculation, or we can actually recalculate from the beginning. It's just a possible way. There are so many formulas in aerodynamics, so we can go several different ways, but we will reach probably the same answer if we are calculating or correctly. So take into account this, I will meet the velocity of 44 meters per second, approximately. It's not exactly 44 meters per second. Okay, so once we are having velocity infinite, 44 meters per second, and we have horde of 0.1 meter, we have Reynolds calculated based on this data, equal to 310 powered by 5, exactly as my experimental data Reynolds number. So I meet the requirement of the similarity function. So this is all about satisfaction of the similarity function. All about satisfaction of the similarity function in our simulation. Okay, so this is how I choose and why I choose horde 100 millimeters in my simulation, and this is why I put the 44 meters per second inside my simulation. Actually, I do not remember now exactly how much I put, because it was a long time ago when I saved the videos, but the idea was exactly this, to satisfy same Reynolds number as we have inside experimental data. Another reason why I have 0.1 meter, because usually in many cases actually, when we test airfoil inside the aerodynamic tunnel, it's manufactured such a way that it has 100 millimeters size of the horde. It's very common, very convenient size of 100 millimeters. It's nice to manufacture. It does not require so big aerodynamic tunnel, and it's enough space to put all the pressure sensors and fixtures inside the airfoil. So it's a nice size to test. Nice size to test. There are also other sizes to test in imperial units defined, but I think 100 millimeter is something nice to be tested inside the aerodynamic tunnel. So this is why actually the incompressible tests are made on similar to this size of the airfoils. These reasons I have chosen to select 100 millimeters horde from point of view of practical applications and point of view of the computational. Reynolds number is 1 order of magnitude lower than Reynolds number in the book and the NACA report, where the experiments were made on Mach 0.3. Look, Mach 0.3 is already on the limit of compressible flow. And if it would be possible, try to use lower Reynolds number so you could have a smaller velocity. The optimal velocity for you would be as small as possible. For example, some 10 meter per second, 15 meter per second, if possible, to have Reynolds number on these values would be great correspondence with experiment. Smaller is the velocity, more reliable will be the result, because less compressibility error you have. If you already work with Mach 0.3, it's we do not expect smaller than 5 or 10, even 10% of error. It will be higher than 5%, definitely, because just compressibility model is giving to us 5% of error in case of when we compare compressible and incompressible for Mach 0.3. I suggest you to use the low Reynolds number as initial data. Low Reynolds number same time means that probably Mach was low, because you remember inside definition of Mach number we have velocity, and inside definition of the Reynolds number we also have velocity. So both of them are proportional to the velocity. Smaller is the Reynolds, smaller probably is the Mach number.